Okay, types of solutions, lecture 78. So we have describe the components of a solution and the types of solutions. So a solution is made up of a solute and solvent. So the solute, and they have this kind of convoluted definition, or I should say complex. In the case of a solution of a gas or solid dissolved in liquid, the solute is the gas or solid. In the case, other cases, the solute is a component in the smaller amount. So generally, smaller amount. And then this is the larger amount of the compounds. It's very rare that you have something, sometimes you get water and ethanol that are mixed in equal amounts. Then you have to decide which one is a solvent and which is a solute. There is only one solvent, but you can have many solutes. And that definitely makes sense. If you take a sample of lake water and you filter out all of the larger organisms that aren't dissolved in there, if you looked at what was dissolved, you might end up finding dozens or even hundreds of things dissolved in the water, but it's just water as the solvent. So you got to make sure that you know the difference between the two. And then we have let's see, so we have the different types of solutions. Well, we can have any two phases can be mixed. So you can have gas and liquid. Gas and solid would be a pretty tricky one to do, but it could still be done. Liquid and solid, gas and gas, very common solution. Air is a solution then. Any gases will mix together. So, and then we have liquid, solid, liquid, liquid. We already did liquid, gas. So let's see, gas, solid. What are we missing here? Solid and liquid, solid and gas. I think that's everybody. Oh, solid and solid. This would be an alloy. So most of the time we deal with solid liquid solutions, but all of them are possible. And if you just want to you can put together any kind of solution that you want from the phases, but the ones that are most useful for us in chemistry are solid liquid, where we take a solid and we dissolve it in a liquid. So we should know that there are a lot of different types of solutions, but for us, almost always it's solid liquid, though gas liquids, where we mix gases together, is also useful. Okay, describe the different levels of concentration in a solution. Well, we have unsaturated, solution, and that means we haven't put in as much solute as the solvent can dissolve. So it means that we're just not there yet. We can keep putting more solute in. We can keep dissolving solutes. And saturated solution, and solution can be written as SOL apostrophe N, can't dissolve any more solute. That's the maximum that we can have. Now there's another type called supersaturated. And what we do to get something to be supersaturated is we heat the solvent, then add the solute. And generally, as we heat up a solvent, it can dissolve more of the solute. And then we cool. So we put in the solute here, it dissolves, cool the solution, and with any luck, for some of these compounds, if they, as long as we're very gentle about cooling it, will keep extra amounts inside of this in the solution. And if you want to get it back out, a lot of times all you have to do is just take a glass stirring rod and slap it against the beaker, and it'll fall out. Or if it won't come out that way, you can take a little seed crystal of the solute that you had put it in there, and it'll immediately come out. And usually they have a pretty good, yeah. So there's a picture in your book of a supersaturated sodium acetate solution. So sodium acetate is pretty much the best compound for creating a supersaturated solution. So you should know that how you make it is we do a little trick. We heat up the solvent, making it more capable of accepting the solute, get it all dissolved in there at a higher temperature, then cool it down slowly, and if the solute and the solvent work together properly, it'll stay in there. A lot of times, most substances won't. You cool them down, and the stuff falls out instantly. But there's some like sodium acetate that work really well. How is solubility affected by temperature and pressure? Okay, so we have two solutions that we want to work with, gas in liquid and solid in liquid. These are the two solutions that we want to work with. For a gas, well, let's do the solid first. As temperature increases, solubility, that is the amount of substance that will go into the solution, increases, generally. There are exceptions to that. So as the temperature increases, solubility increases, and then as T decreases, solubility decreases. But for gases, as the temperature, now I should say, the reason that happens is the temperature goes up, the solvent molecules move faster, they have more kinetic energy, they have an easier time breaking apart the solid and keeping those ions in solution. So it's really allows the solid, gives the solid that extra energy to break off from its bulk and go into the solution. But as the temperature increases for a gas and liquid, a gas dissolved in a liquid, as temperature increases, the solubility decreases. And then as the temperature decreases, the solubility, and solubility can be abbreviated as S. As the temperature decreases, the solubility increases. Now, what's happening there is that the gas molecules just are guests in the liquid. They happen to like being in the liquid. They're attracted to the liquid, the say it's water. They're attracted to the water molecules, but they're still gases at heart. So if you increase the temperature, you increase the speed at which those gas molecules are moving. When they get to the surface, they're going to escape. So it's already kind of a dicey thing keeping a gas inside of a liquid. If you increase the temperature of the solution, the liquid molecules move a little bit faster, but the gas molecules increase their speed drastically. So they will escape a lot faster. So it's you just kind of scare them out because they are moving so rapidly now that they can't stay in the liquid. So as you decrease the temperature, the solubility for gases increases. And you may have noticed that with, say, pop. If you start it with a cold pop, cold Coke or Sprite or whatever, and you open up the cap, there'll be that release of CO2. But if you let it sit and it's warm and you open it up, a lot of times it'll just come out in a fountain, just by the slight movement of opening up that cap will cause that, because the gases are no longer very soluble. Now that's temperature. Okay, so for pressure, as the pressure increases or decreases for a solid, as pressure increases or decreases, no effect on a solid and a liquid. The solid and the liquid could not care less about the pressure. Even very high pressures of hundreds of atmospheres will have no effect on a solid or a liquid. But as the pressure increases as pressure increases, assuming that the pressure that's increasing is the gas itself that's above the liquid, the solubility increases. As pressure decreases, the solubility decreases. So we're talking about the pressure, the partial pressure of this gas above the liquid. As that increases, you just have more of those gas molecules above the liquid, and so you're going to get more of them. Since there's a certain chance each one will go into the liquid phase per second, if you have more of them in the gas phase, more chances you have. So the more that will go into the liquid. So when they're trying to put CO2 into these carbonated beverages, they just increase the pressure above the liquid to between 5 and 10 atmospheres of CO2, and that drives the CO2 into the liquid. So you should know how temperature and pressure affect a solution that is a gas in a liquid and a solution that's a solid in a liquid. Now, we talked a little bit about this, but we didn't have a name for it at the time. But how are ionic compounds dissolved in solution? So this is you have sodium chloride, say. It's very soluble in water. So it's this big lattice work of ions. And when this goes into, you put this into water, the water molecules are attracted because they're this is slightly positive, this is slightly negative. The slightly positive side is attracted to the negative ion. And these water molecules will attract the Cl minus until it goes into solution. I'm going to put it down here. And the Cl minus ion, it will then be wrapped up with water molecules on every side, and the thing that's attracted to them, or that holds them together, are the hydrogens, the slightly positive side of the water. It creates a cage around the ion. This is called hydration. And then the sodium feels the same effect, except that it's the oxygens of the water that are attracted to the positive side of the positive charge of the sodium. So these hold them intact. They create a stable structure for the ions to go into solution. The ions love being part of the ionic compound, but here they get to be completely wrapped up in water molecules, which is even more stable than being part of the lattice. So there's ionic compounds that are very soluble because they are easily wrapped up by the water molecules. They like being part of that. They like having that hydration effect. But some ionic compounds, have such a strong attraction to each other. The ions are so strongly attracted that the water can't get to them. So that's where you get the insoluble compounds, because the lattice energy is stronger than the hydration energy. Okay, so we should know that. And then, so I kind of took that a little bit out of order, but so because the solubility, the temperature and pressure changes are here. Sorry about that, but now we're back on course, and we have Henry's law. And I won't give you a calculation with this, but you should understand what this equation is saying. Henry's law says the solubility of a gas in a liquid is equal to this constant we just call Henry's law, the Henry's law constant, and then this P is the partial pressure of the gas. What it's saying is that the solubility of a gas in a liquid is proportional to the partial pressure of the gas over the liquid. Should have written that out beforehand, but that's what it's saying. So you should know that there's a relationship between solubility and partial pressure, and we mentioned it. I mentioned it earlier, but here's the equation that governs it. You can see as whatever this KH is, and it depends on the gas, so we don't have to worry about that, but it's some positive number. As the pressure goes up, the solubility goes up. As the pressure drops, the solubility drops. So just be able to either state the Henry's law and write out what each term is, but you should also be able to say how the solubility of the gas is affected by the partial pressure. That's what I'll be looking for.